thank you for the introduction, and thank you very much for the invitation to speak at this conference. So as the title suggests, I want to explain the derived equivalence classification of Brauer graph algebras, and this is based on a joint work with Sebastian Opper. So let me start with the definition, so what a Brauer graph algebra is. And we start with an oriented surface S and a graph gamma on the surface. And so the embedding of gamma into the surface gives a cyclic ordering of edges around each vertex of the graph. And the additional piece of data is the multiplicity function. So at each vertex of the graph gamma, we have a natural number. So these are not the names of the vertices, these are the multiplicities of the vertices. And to this data, we can associate a quiver with relations, so Q gamma and I gamma. And then any Brauer graph algebra can be constructed as a path algebra with this relation. So B will be the Brauer graph algebra. And I'm considering only algebraically closed fields. So how do we do the construction? So the edges of the graph gamma correspond to the vertices of the quiver, and the cyclic ordering of edges around vertices gives arrows. So if we have two arrows which follow each other in the cyclic ordering, then we draw an arrow. And the ideal of relations is also constructed easily from that. So in the quiver Q gamma, we see that the arrows are divided into cycles, which correspond to the vertices. And so if we go from one cycle to another cycle, then this is 0. And the same holds if we go along one cycle not in the cyclic ordering. And this is one type of relations. And another type of relations is that if we take an edge, there are two vertices attached to this edge. And then if we go around one cycle, the number of which corresponds to the multiplicity times, then it's equal to going around the other cycle the corresponding number of times. So this is the definition of a Brauer graph algebra. And well, Brauer graph algebras, they were studied quite a lot, and they coincide with symmetric special biserial algebras. So we know the classification of modules, we know the Alexandra-Zvonareva quiver, and so on. And also I can say, I want to mention that they originally come from modular representation theory. So blocks with cyclic or dihedrodifferent group, they are examples of Brauer graph algebras, and same blocks of Hecke algebras are also examples, and so on. So now I can formulate the theorem I want to explain, and this is due to Antipov and Opper and myself. So if we, okay, sorry. One last thing I wanted to say here is that if we choose this embedding in a minimal way, so that the surface is cut by our graph into annuli, then this S is actually unique. And then when we cut the surface into this annuli, we can consider the faces of the graph gamma. And we can also consider perimeter of a face, so the number of edges we go along to cut out this annuli. So now I can formulate the theorem. The theorem says that two Brauer graph algebras, B and B prime, are derived equivalent if and only if the following conditions hold. So 1, 2, and 3. And so first, the number of vertices, the number of edges, and the number of faces coincide, which tells us that the surfaces corresponding, so this minimal surfaces corresponding to gamma and gamma prime are homeomorphic. Then the multisets of perimeters of faces and the multisets of multiplicities of vertices should also coincide, and also bipartivity of gamma and gamma prime. So they are either both bipartite or they are both non-bipartite. So that's the theorem. And so who did what? Antipov introduced this invariance and proved that they are indeed derived invariants. And then Sebastian and myself reconstruct the equivalences. So we take two algebras with this coinciding invariance, and we produce a derived equivalence between them. And then there were a couple of results of a similar flavor before. So Rickett proved this theorem for Brauer tree algebras. So the graph of the algebra is a tree, and there's at most one non-trivial multiplicity. And these are precisely Brauer graph algebras of finite representation type. And then Antipov proved this theorem for the case of the sphere. So when the surface corresponding to the graph is a sphere with boundary components. Okay, so let me try to say a couple of words about the strategy of the proof. So one of the main ingredients is the connection between Brauer graph algebras and Gentile algebras. So due to a theorem by Sebastian, Brauer graph algebras are trivial extensions of Gentile algebras in the case of trivial multiplicity. So when all the multiplicities at the vertices are equal to 1. And how do we go between Brauer graph algebras and Gentile algebras? So we choose an arrow at each cycle corresponding to a vertex. So here they are denoted by green. And we consider an ideal generated by these arrows for each vertex, and we take the quotient. And this can be depicted by dragging these vertices to the boundary component corresponding to this arrow. And this would produce a Gentile algebra. And to go in the opposite direction, one takes the trivial extension. So the same as in the talk by Jen. Okay, and so the recently Gentile algebras were also classified under derived equivalence, and one of the things that helped to do that was to enlarge the class of Gentile algebras to include some infinity algebras, and then the construction of derived equivalences was easier. So how does one do that? So we have this surface, and then the surface can be equipped with a line field, and this produces a grading on the curves which correspond now to the edges of our graph, and this also produces infinity operations. And in this bigger class of algebras, one can produce derived equivalences by simply adding additional edges. And this is quite a simple geometrical procedure, so one can do something. And this is due to a lot of people, so Haydn, Katakov, Kontsevich, Likili, Polishuk, Opper, Plamondon-Scholl, Amiot, Plamondon-Scholl, and Opper. And we want to follow the same strategy for Brauer graph algebras. So we want to enlarge the class of algebras so that the construction of derived equivalences becomes simpler. And we do it in the following way. So the same as in the case of Gentile algebras, we equip the surface with a special kind of line field. And then we can also drag this line field along a cut to produce Gentile algebra. And then we can take an A-infinity trivial extension of this corresponding non-classical Gentile algebras. And this produces a larger class, which contains a class of Brauer graph algebras with trivial multiplicities. And then to produce Brauer graph algebras with higher multiplicities, we can consider branched covers of the surfaces, and then we can drag, we can lift the graphs to the branched covers. We can lift the line fields, and then we can consider the action of the Dirac transformation group and the orbit category. And this will give us a construction of a larger class of infinity algebras, which contains the class of Brauer graph algebras with non-trivial multiplicity. And this can be considered as an infinity version of the work by Green, Schroll, and Snashel, and Sashiba. So this was done for the usual Brauer graph algebras. These multiplicity-free covers of Brauer graph algebras were already considered. Okay, so we have enlarged the class of algebras we are considering, and now we can obtain that in this larger class, adding edges gives a derived equivalence again. And after that, we can deduce that Brauer graph algebras corresponding to the to orbit, so they are basically defined by orbits of line fields under the mapping class group action, and then we can use the classification of this orbits of line fields due to Likili and Polishuk to match their invariants to our combinatorial invariants and get the theorem. That's all.